Welcome. So this question says a 200 degrees C spherical body has a surface emissivity of 0.3 and a radius of 4 meters. How much power does it dissipate? So visualize, here we have the object and it's got a certain temperature and it is radiating energy. Even though we can't see it glowing, it's going to be radiating a different color depending upon its temperature. Not the color that you see reflected. This is if you put it in the dark, could you see a color? And we can't see the radiation from low temperature objects, and we can't see the radiation from very high temperature objects. We can see the radiation from objects that are about the same temperature as the sun, or within a range of that. But even an ice cube glows. It's just with a colour that's redder than the reddest red than we can see. And so that's what this is about. So we have this, it's 200 degrees C. So T is equal to 200 degrees C. And immediately I'm going to change it to 200 plus 273 Kelvin. When you're dealing with ratios of numbers, it's always best to deal with Kelvin, unless you've got a good reason not to. You should be in Kelvin. And then the emissivity. This is a fractional number going from 0 to 1, 0 being the mattest black you can imagine, and 1 being the whitest, glossiest white you can imagine. And this is 0.3. And then the radius of this, so the radius equals 4 meters. As the radius of that is 4 meters. And it's asking how much power is dissipated. So we need to know the expression. This is Stefan's law. Power equals sigma A eta t to the fourth. It's a very unusual relationship, having something to the fourth. We don't see that very often. So power is equal to our sigma. This is this number here. It's 5.7 times 10 to the minus 8. It's a constant proportionality to make the numbers work out. And then A, well, A of course it's a sphere, so the formula for a sphere is 4 pi r squared equals the surface area of a sphere. So this would be 4 times pi times, that would be 4 squared. Yeah, 4 squared. And then my eta is this fractional term, which is 0.3. And then I have my t to the fourth, which is 473 raised to the power of 4. 473 because, of course, it's 200 degrees C plus the conversion to get it down to Kelvin. 0 degrees C is 273 degrees Kelvin, etc. So the rest is just calculator work, really. Got to go step by step. So I'll get my calculator. 5.7 second EE to the minus 8. Put that guy in, enter. And then times 4, enter, times pi, enter, times 16, enter. And then times 0.3, enter. And then we go times bracket 473 caret 4 bracket, enter. And I'm getting 172,096 watts. So there's my answer. 172,096 watts. So you can imagine if I increased my surface area, I would get more power dissipated because there's more surface radiating. If I change my temperature, this is a very strange relationship. If I doubled my absolute temperature, I would get 16 times the amount of energy per second radiated. Or put it another way, if I want to maintain a temperature which is twice the absolute temperature, I have to provide 16 times more energy per second to achieve that temperature. And that's why hot stars, say 10,000 Kelvin, burn out so much quicker than medium stars, say 5,000 Kelvin, because they require 16 times the amount of energy per second to be created from fuel, but they don't have 16 times the amount of energy, amount of fuel in them, and so they tend to burn out. So that's why blue stars tend to burn out much sooner than yellow stars or red stars. So there we have it.